So it's now time for another 4 short talks. And the first one is Tang from LMU in Munich. So over to you.
Hello, everyone. I'm Le, and from LMU, SPIN PhD student. So today I'm joined talk about my topic, the local seismic anisotropy from 6C observations. So let's look at the azimuth anisotropy, and there's 2 directions to study this topic. The first one is the time-dependent tomography. So this method has very good depth resolution, but has very poor lateral resolution because of the effect of the heterogeneity. So the second method is using the single station method. For example, the shear wave splitting, and this method can provide a very high lateral resolution, but a very poor depth resolution because of it provides the average result for the whole depth. So the question is that can we consider these 2 resolutions simultaneously? And in isotropic media, so we can do the ratio between the translation and the rotation. We can get the localized phase velocity. So the question is that can we do this in anisotropic media? Yeah, in the assumption is the weakly anisotropic media. So in this assumption, the analytical solution has this expression. So what we found is that the ratio is equal to the analytical solution in weakly anisotropic media. So I'm not going to talk about the detail, just let's directly look at the observation. So I select 3 seismic arrays in Southern California, and using the array-derived rotation to retrieve the rotational waveform. And look at the observation, and the phase velocity, what we got is matches the 2% anisotropic tier. So, and the frequency range, the most sensitive depth of this frequency range is the ionosphere. So this depth, which means that the faster direction of the relay wave is consistent with the plate motion direction or the mantle flow direction. And we can find the faster wave direction of the 3 seismic arrays. And we compare the result with the previous result using other method. So the red arrow is the direction of the absolute plate motion, and the black line is the faster direction combine the surface waveform and the SKS splitting data. And the dashed red line is the San Andreas fault, and the red arrow indicates the plate motion direction. So if we put our result here, the 3 seismic array, and we can find the faster direction of from a 6C result. Actually, it is consistent with the plate motion direction in each point. So the interesting thing is that the 3 seismic arrays are within 1 wavelength. Even the 3 seismic arrays are within 1 wavelength, but they have very different result, which means that it has very high lateral resolution, and the resolution is much smaller than 1 wavelength. Yeah, because of a limit of time. Yeah, I just concluded the topic. And we proposed a new method to study the azimuth anisotropy. Yeah, it has very high lateral resolution. It's much smaller than 1 wavelength. So the second question is that we have to improve the observation of the rotation, because I use array-derived rotation because we don't have available rotational sensor. Yeah. So the third is, and I'm trying to test the ambient noise data, but in theory, it works. But for the real data, we have to do a lot of tests, but should be possible. Yeah. That's it. Thank you.